Good morning, student. In this part of the video, we are going to learn about solenoid and toroid. Okay. First let us discuss what is solenoid and toroid. Okay. What is solenoid and toroid? A special kind of it's a special kind of arrangement to create or produce magnetic field. Okay, and the shape of the solenoid is actually a cylindrical shape, and the toroid is solenoid, and a toroid is a circular shape or in the form of ring. Okay, circular shape. This is toroid. Okay. Now you see cylindrical shape, circular shape, these are all symmetrical shape. Okay, so we can very easily calculate the magnetic field in a solenoid or toroid using Ampere's law. Okay, so solenoid and toroid are two cases where we again going to use Ampere's law. If you remember, in the last class I discussed the application of Ampere's law for a infinite conducting wire, which is a cylindrical shape. Similarly, the solenoid is also a kind of a cylindrical shape, or toroid is in the shape of a circle. So basically what we can do, we can apply Ampere's law easily in order to calculate the value of the magnetic field. Okay, let's first discuss about solenoid. Okay, now what is a solenoid? Suppose first you take a long conducting wire, and then what you have to do, you have to turn the wire in the form of a helix. Okay, this is the form of a helix, right? Okay, now you see, now you let current I passes through this arrangement. Okay, now this arrangement will be termed as a solenoid. Okay, suppose you initially you have a L length of wire, and now what you have done, you just reshape the wire with n numbers of closely spaced turn in the form of a helix. Okay, so this arrangement, now we can call this as a solenoid. Okay, suppose there are n numbers of turns here, and each turn we can now consider it as a circular loop, because you see it's in the form of a helix, but every turn here we can consider this as a circular loop. Okay, so you see, now if you suppose now a current I is flowing through this solenoid. Okay, then the net magnetic field, you see we always use current in order to produce a magnetic field, right? So if you flow a current I through the solenoid, then the net magnetic field will be the resultant field due to the n circular loop, because the solenoid of length L has we say let's a small m number of circular loop. Okay, so each circular loop will contribute towards the magnetic field. Therefore, the magnetic field produced by the solenoid is due to the total magnetic field, total B, will be the vector sum of the magnetic field of individual circular loop. Okay, because we have converted the L length wire into a n numbers of circular loop, and this arrangement is known as solenoid, and we let the current I through the solenoid, then each current loop will produce its own magnetic field, and therefore the total magnetic field of the solenoid will be due to the vector sum of all the magnetic field due to its turn. Say this turn produce magnetic field B1, this turn B2, B3, B4, like that. So the net magnetic field will be the sum of all magnetic field B1 plus B2 plus B3 plus dot 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 dot. If there are n terms, then n number of magnetic field. So basically we have to add up all this magnetic field. Okay, so a straight wire we have converted into n circular loop in the forms of a helix. This is the arrangement of a helix where all the neighboring loops are closely spaced. Okay, the best example of solenoid, as you can think, is your ball pen spring. In ball pen spring, if you little pushed apart all the ring, if you little pushed apart, then it will be in a nice helical form. Okay, so that arrangement we can consider it as a solenoidal arrangement. Okay, now what we are going to do, we are going to see what is the net magnetic field produced by this kind of arrangement. This kind of arrangement will obviously going to produce a magnetic field, and this magnetic field will be different from produced by a long straight wire, because now we have reshaped the wire in the forms of a helix having n number of circular loop. Okay, so this magnetic field will be very different from this magnetic field, and we are going to find out what is the value of the magnetic field and where is its direction. Okay, that thing we have to find out. Okay, for that what you need to know the value, the direction of the magnetic field as produced by a circular loop. For example, if you remember, if we consider a circular loop and it's carrying a current in the anti-clockwise direction, then the shape of the magnetic field, if you remember, it was the shape was like that. Okay, the field lines were like this only. Okay, and there was very small magnetic field around the circular loop. The maximum amount of magnetic field was along the axial direction. Okay, so for circular loop, the maximum amount of magnetic field you will find in a direction passing through its center and perpendicular to the plane. That means it is the axis of the circular loop. In this region, or on the left and right in the figure, a very little amount of magnetic field will be present. Okay, so now you see this solenoid, it consists of n numbers of circular loop. Okay, so for each circular loop there will be this sort of magnetic field. Since this loop is along this direction, so basically the magnetic field will be like this. Okay, the magnetic field will be like this. This kind of magnetic field will be there. Okay, now in this region, just above or below the circular loop, there will be a very little, almost negligible amount of magnetic field will present. As I'm saying it negligible because the magnetic field in the axial direction will be much stronger than the magnetic field in this region or at that region. So for our purpose, we can basically ignore the magnetic field above or below. We are just going to consider the magnetic field in the axial direction. Okay, so for one circular loop there will be this kind of magnetic field. So for each circular loop, you see each loop has same radius and same amount of current will flow through each loop. Therefore the magnitude of the magnetic field produced by each loop will be similar. Okay, so the magnetic field due to a solenoid will be always in the axial direction, always will be in this direction. Okay, so magnetic field on above or below the solenoid, it's very negligible, and if it is an ideal arrangement, but since it's a helical arrangement, not a perfect circle, therefore there will be always a little bit of magnetic field just below or above the solenoid, but for our purpose we can neglect it, and we can say that the net magnetic field will be always in the axial direction, because you see all this magnetic field for this circular loop here, there will be another circular loop for this also, there will be magnetic field like this. So all this magnetic field in the x direction, if we say this is the x direction will add up, and therefore we can say the magnetic field will be along the axis of the solenoid. Okay, now what we are going to do, we are going to find out the value of that magnetic field. Now we know the magnetic field along the axial direction, and now we are going to determine the value of the magnetic field. Okay, So in next part, what we are going to do, we are going to calculate the value of the magnetic field due to a solenoid. Okay. Okay. So let me redraw the schematic of the solenoid with magnetic field. Suppose. Because solenoid is in the shape of a cylinder, because if you look at this I mean, you can say it's like a cylinder, right? Like a cylinder. Okay. So let me concentrate on one cross section. Suppose we are concentrating on this region of the solenoid. Okay. So let's say okay. Now if you see one part of the solenoid, you see, so in this region we can say that the current is entering, and at this region we can say that current is leaving. Okay. So if we suppose this part the current is entering, so we can symmetrically show this part as like this symbol. The cross symbol will represent that the current is entering in this region and the current is leaving at this region, right? Okay. So there are n numbers of turns like that. In suppose if I say if I show you a one turn, say this turn is like this. Okay. So here, because the current will flow across the turn, right? So in this direction the current is entering, so I am putting a cross symbol here, and in this direction the current, we can say that the current is leaving. Okay. So this part will be shown by dotted line. Okay. So this dot and cross, these are not the direction of magnetic field but the direction of the current. In one part current is entering and another part the current is leaving. Okay. So it represents basically this thing. Now we know that the direction of magnetic field is along the axial direction. So these are the axial direction of the magnetic field. Okay. The magnetic field will be along this direction. These are the direction of the magnetic field. Okay. Now what we are going to determine, we are going to find out the magnetic field at a point P, say on the axis of the solenoid. Suppose we are going to find out the magnetic field at this point. Okay. Now to find the magnetic field we have to use Ampere's law. What was Ampere's law? Ampere's law was B dot dl, line integral, closed line integration B dot dl mu naught into I inclusive. Okay. As I told you in the previous class, the first thing to do apply the first thing in order to apply the Ampere's law, first what we have to do, we have to consider a Ampere's loop. Okay, and Ampere's loop we have to choose such that it encloses the current element. Otherwise there is no point of using the Ampere's law to calculate the magnetic field. Okay, so now you see it's in the shape of a cylinder, so probably we can take a rectangle or cylindrical region as a Ampere's loop. Okay, and suppose we are taking a Ampere's loop like this, passing through the point P. So where we have to determine the magnetic field, there the Ampere's loop has to pass it. Okay, so we are taking Ampere's loop like this. It's a cylindrical shape, and we are taking the Ampere's loop in the form of a rectangle or a square, so that it's almost a similar type of almost a symmetrical shape is there. Now for this Ampere's loop we are going to apply the Ampere circuit law. Okay, and before that let me do a little bit of calculation. We assume, let's suppose this the length of the Ampere loop is h. Okay, this length is h, and this part is not that important, so I am not giving it any name. Suppose h is the length of the Ampere's loop. Okay, so before so suppose there are small n number of turn per unit length of the solenoid. Because you see this all this circular loop will be closely packed, and we assume that there are a small n number of this kind of loop per unit length. One unit length, it may be a meter or it may be a centimeter. There are small n numbers of loops. Okay, so we are considering what is the length of the Ampere's loop. We have considered h. Therefore number of loop in length h will be equal to n into h. Isn't it? Small n is the number of turns per unit length, and the length of the our Ampere's loop is h. Therefore number of loop in length and h will be equal to n into h. Now each loop carry a current I. Because each loop there is a current I, same current I flows through each loop. Therefore total current enclosed by the Ampere's loop is equal to n h into I. Okay, small n is the number of turn per unit length, h is the length of the solenoid, and I is the current in its loop. You see, in this portion, in this Ampere's loop, there will be how many closed loop? There will be nh number of closed loop, because n is the number of turn per unit length and h is the length of the solenoid. Therefore number of loops will be, this kind of loop in this portion will be n into h, and each loop carry a current I. Therefore the current enclosed by, because you see these are the current which entering into the Ampere's loop, so the total amount of this current is equal to n h into I. Therefore the expression, in this expression, I inclusive is equal to n h into I. That's we have already found. Okay, now basically what you have to do, you have to just you have to find out this product line integration B dot dl, then you can determine the value of the magnetic field. Okay, now as I have already told you, I am going to do this line integration in the anti-clockwise direction. Okay, so first we are going to starting from here to here, then here, then this part, and then again this part. In this way we are going to do the line integration. Okay, now in this direction the length element direction is dl in this direction. Here the length element is dl along this direction. Here the length element is along this direction, and here the length element is along this direction. Okay, but you see, if you say A, B, C, D. Okay, in the region AB, the length element and magnetic field will be in the same direction. Okay, so B dot dl is equal to only B dl cos 0, because the same direction, B d into l. Okay, now in this direction, length element is in this direction and magnetic field is perpendicular to it. Therefore B dot dl will be equal to 0. So for AB, B dot dl is equal to B dl, right? For BC, B dot dl is equal to 0. For CD, now you see this region is outside of the solenoid, and I have already told you outside of the solenoid we don't have to consider the value of the magnetic field, because it's very, very weak. We can neglect it for practical purpose. Therefore for CD B dot dl is almost equal to 0. Okay, and for dA again the magnetic field is perpendicular to the, because this is the direction of dl and this is the direction of magnetic field, so magnetic field is perpendicular to dl. Therefore for dA, B dot dl is equal to again 0. Okay, therefore we can write surface in line integration B dot dl is equal to what we have written, mu naught n h into I. Okay, so B line integration dl is equal to mu naught n into I. Okay, and now you see what is the value of the line integration B into dl, because you see only this part, only the part AB will remain. BC, CD, BC and DA, it does not does not make any contribution. So in this case the integration, line integration dl is nothing but the length of the side AB, because BC, CD and DA, it doesn't contribute at all. So we can neglect all this part, and only the part contributing to the magnetic field will be the line element AB. Okay, so we can write line integration dl is nothing but this part AB. Okay, so what we can write is B, and the length of AB is nothing but the length of H, because we assume that the length of the solenoidal loop is equal to H. Okay, so BH is equal to what we have find, mu naught Ni into H. Okay, so if H's get cancel out, what we'll find that B is equal to mu naught N into I. Okay, so this is the value of the magnetic field due to a solenoid having number of turn per unit length N and the carrying a current I. Okay, so you see, suppose you are given a solenoid and you are told that there are, say, suppose 1000 turns are there, and the current flowing through each turn is equal to 1 ampere. So number of turn per unit length is N, and there is 1 ampere of current. So the value of the magnetic field will be equal to B is equal to mu naught is equal to 4 pi into 10 to the power minus 7 Tesla, and number of turn per unit length, say 10 to the power 3, and this is, say, 1 ampere current is flow. Okay, so this value will be equal to 4 pi into 10 to the power minus 4. This is Tesla. Okay, so this much of magnetic field that solenoid will produce. 1 ampere current and passing through a solenoid having the 1000 numbers of turn per unit length, say per unit meter, thereof n numbers of turn, then it will produce a magnetic field equal to 4 pi into 10 to the power minus 4 Tesla. And the direction of the magnetic field is along the axial direction. For example, if the solenoid is like this, okay, and the magnetic field will be inside the solenoid in the axial region. Okay, so you can use this magnetic field to do many things. In many applications, when we need a magnetic field, we just use a solenoid to create that magnetic field and use that magnetic field in order to do various purposes. Okay, so finally we found that the magnitude of the magnetic field mu naught into N into small I. Okay, and in the axial direction, Okay, here small n is what? Numbers of turn per unit length of the solenoid. Small I is what? The current passing through the solenoid. Each because the same current will pass through each loop of the solenoid. Therefore, we can say I is the current in each loop of the solenoid, and mu naught is a constant of permittivity of the free space that we know. Therefore, using this very simplified expression, B is equal to mu naught Ni, we can calculate the magnetic field for such type of solenoid arrangement. Okay.